this webinar to let people a chance to see it if they do not have the opportunity to join us today. So thanks again, Fiona, and please, the floor is yours. Share your slide, and we have basically at maximum 1 hour in front of us. Thanks.
Okay, great. Thanks, Gail. Hi, everyone. Thanks for taking time on your Monday afternoon to come to this seminar. So I'm presenting results from a paper that we've got submitted in Earth's Future at the minute on multi-centennial projections of global mean sea level rise and their application. And then the co-authors are listed here, most of them in Protect, a couple of PhD students at King's. So hopefully I don't need to really give much motivation as to why we're doing this, considering it's a Protect seminar. But basically the IPCC have been given ranges of future sea level rise, and the latest one, AR6, was the first one to give likely ranges up to the year 2150. However, the longer term projections they gave at 2300 were only a summary of the literature using this P-box approach, and they couldn't rule out this sort of high sea level rise of up to 15 meters over the long term. So our work basically was looking at this and trying to come up with some probability distributions that go up to 2300 and past that, and give a sort of more detailed idea of what sea level rise would look like. And then another sort of issue with IPCC is that they're only giving these intermediate scenarios up to 2100, 2150. They're not giving it on the longer term. So that was also something that we wanted to address. So the work in this paper was based on the deliverable that King's led in 2021. So there we used projections from DeConto et al. For Antarctica, Andy Ashvanden's work for Greenland, and then the AR6 report for all of the components. However, we chose to take a more detailed approach for the paper and use some more data that either became available or that we found after that. So the general aims for the paper was that we wanted to produce probabilistic model-based projections for global sea level rise. We wanted to extrapolate projections from 2300 to 2500. We wanted to include intermediate emission scenarios that haven't been often used when doing these multi-centennial projections. And then we wanted to consider the use of these projections for stakeholders. So when it came to choosing our methods and the models that we'd use for our projections, we made the following choices. So we chose projections from physically based models, and in particular, we emphasized choosing perturbed parameter ensemble studies over sort of not physically based projections. We made the assumption that RCP 2.6 and RCP 8.5 correspond to the SSPs with similar radiative forcing at 2100. This was because there was a lot of data available sort of for one or the other, and sort of just choosing one sort of emissions pathway to go with would have meant we'd have had even less data than we had for this. And we chose not to build projections under SSP 585. So this was because the current NDCs are falling well below this trajectory. So we felt that it was unrealistic that we'd still be following this pathway up to the year 2500. And initial extensions we did of this scenario for the deliverable contained large amounts of uncertainty and really high emissions that we don't expect to continue. So as the Antarctic ice sheet is the most uncertain contributor and has uncertain processes characterizing contribution to sea level rise, we chose to use 4 different studies when creating these projections. So we used Bulthouse et al. 2019, which used Fetish to generate RCP projections to the year 3000. We used DeConto et al. 2021, which was the only study to contain the marine ice cliff instability, which is obviously a major factor when it comes to the Antarctic contribution. We used Larry et al., which used PISM and emulation techniques to generate projections to 2300. And finally, we used the extension of Lieberman et al. That was generated for AR6, where they applied linear response theory to 69 sheet models. And this originally was to 2100, but was extended to 2300 using SSPs for the IPCC report. For the Greenland projections, we used Andy Ashvanden's work. So despite the IPCC not including it due to their high projections at 585, we wanted to use this work as it was the only data that went out to 2500 for Greenland. Their intermediate scenarios were more in agreement with IPCC than its high ones, and we wanted to reflect the uncertainty that it presented with its surface processes work. And then we also used the AR6 projections, where they fit statistical models to simulations to 2100, which was then extrapolated to 2300. So despite the lack of physical modeling between 2100 to 2300, we used it here so that we had something to sort of counter the results from Ashvanden et al. So for the ice sheet contributions, we chose to use a simple statistical extrapolation method. So these all, apart from the Bolthouse for Antarctica and Ashvanden for Greenland, sorry, went to 2300. So initially we considered using a simple linear method, but thought that was deemed unsuitable due to the expected declining radiative forcings after 2300. So instead, we assumed that the rate of ice mass loss generally was likely to decrease. So what we did was we interpolated data to annual values, and we then fit a linear regression to the last 50 years of the data. So sort of where this curly bracket is. So we found what the rate of ice mass loss was from 2250 to 2300. We then extrapolated using gradients sampled uniformly between 10 and 100% of the gradient of those last 50 years. And that was to represent a slowing rate of mass loss. So here you can see that there's an obvious decline in sort of a linear fashion from 2300 onwards. And then we sort of use that range to look at what the projections would be. For other contributions, we use a slightly simpler technique. So for glaciers, we used the AR6 numbers. We extrapolated linearly from 2300 to 2500 here, with a cap applied to total contribution, which we took from Farinotti et al. For thermal expansion, we estimated from AR6 projections using a 2-layer simple climate model. And for the land water storage, we extrapolated from 2300 to 2500, assuming that there was no further net contribution beyond 2300. So those numbers just stayed level. For summing up into total global sea level rise, we built all contributions so that they were probability density functions, so distributions rather than single values. AR6 projections were made relative to 1995 to 2014, and other studies were relative to 2000 or similar. So we chose to standardize to a baseline of 2020 for consistency. We calculated global mean sea level by assuming that all contributions are fully correlated. So we could just perform a simple sum of all quantiles. So a more sophisticated method could be used in future, and this is something that we discussed in the discussion section of the paper. Okay, so some actual results. So these were our Antarctic results. So on the left in blue, you've got SSP 126, and on the right in orange, you've got SSP 245. These are the time series. So the bold is the average projection, and then in different patterns, you've got the 4 different studies. So the 4 sets of projections are varying really widely. So the contributions are lowest for Bolthouse et al. For both scenarios. So they're giving a median sea level rise at 2500 of 0.19 meters for 126 and 0.53 meters for 245. The highest contributions are different for each scenario. So for DeConto et al., they're the highest for 126, giving 1.5 meters, but for 245, Lowry is given the highest at 2.47 meters. So we just performed a simple average of these 4 studies to come up with the bold projections, and that was giving us a median of 0.86 meters for SSP 126 and 1.44 meters for SSP 245. So considering why there was such a difference between projections, we thought that DeConto et al. Is the only one to include Mickey. So this in particular would influence longer term projections, which is a reason why it was giving much higher contributions. Lowry et al. Had a really large response under a constant model climate. So the high projections may be due to a model drift that they didn't account for. Snow accumulation can vary really strongly between climate models. So again, Lowry et al. Used a GCM with a relatively low snow accumulation, which might contribute to their higher estimates. And then there's the fact that different scenarios were used. So the Bolthouse and DeConto work was done using RCPs, and the Lieberman and Lowry work used SSPs instead. And although we are treating them equivalently, there are some small differences between them. So for the Greenland results, we found, again, a clear difference between the 2 scenarios. So especially under Ashvanden's projections, there was a doubling of projections between SSP 126 and 245. So that went from a median of 0.58 meters for SSP 126, and then up to 1.21 meters for SSP 245. It also had a much broader range at 245, showing there's a lot more uncertainty for intermediate emission scenarios. And then the IPCC report was a lot less uncertain, but that's to be expected due to the constant mass loss that they had between 2100 to 2300, rather than the SSP extensions that Ashvanden used. The glacier results, so we found that for SSP 245, the world's glaciers are projected to disappear by the year 2260, and we found a likely range of 2190 to 2439. Under the low emission scenario, there's still some possibility of complete disappearance at some point after 2200, but this is not as likely. For the thermal heat expansion, we found that the contribution doesn't increase much beyond 2300, and this can be explained due to the decline in forcing that we're expecting after 2300, and the fact that there's a relatively fast response to climate change under the thermal heat expansion compared to the slower response that you're getting from ice sheets. For the land water storage, as I said, we held this fixed from 2300 onwards. So the median projections are 0.07 meters for the low emission scenario and 0.11 under 245. But again, this was a sort of a minor contributor to sea level rise. So then we summed these together to come up with our global mean sea level rise results. So for the low emission scenario, this is 1.98 meters by the year 2500, with a 95% range of 0.83 to 3.38. And for the intermediate scenario 245, it was a median of 3.38 meters, and then a wider range of 1.72 to 5.85 meters. So considering the limitations to this study, sort of as discussed before, there was a relative lack of multi-centennial scenario-based projections. So we managed to find 4 for Antarctica and 2 for Greenland. And then we're using the AR6 data for all the other contributions. Our simple extrapolation technique from 2300 was similar to sort of other studies that have used constant rates, but could have been done in a more sort of sophisticated pattern. So as has been done in other studies, we could have done a statistical modeling of the contributions as a function of global surface air temperature. But we were concerned that this would be interpreted with undue confidence with people. Like, we're aware that this is quite a simple study and we didn't want people sort of fixating on these numbers and using them sort of too confidently. Sorry, what's the question mark for? Okay.
Yeah, nothing in particular. I was just wondering why this annotate was there. Sorry.
Sorry, the L?
Do you hear me?
Yes, I can hear you. Sorry.
No question.
Oh.
Nothing at all. I was just wondering why this annotation was there. I'm not supposed to be able to touch that, I think.
Okay. Yeah. So the method we used to combine studies and sea level projections, again, was quite a simple approach. We considered doing a more conservative approach, sort of such as the P boxes used by AR6. And sort of our method of averaging quantiles does mean that our projections are much narrower than those that the IPCC reported, as they're sort of using the most conservative approach possible. We assume that all contributions are fully correlated, mostly for sort of ease of summing them. I think in future we won't be doing this, as we're aware that there's a good chance that the climate changes aren't affecting all contributions equally. So for example, land water storage isn't directly related to warming, and it may well be that the Antarctic accumulation is anti-correlated, as we still don't have sort of a sign of change assigned to Antarctica by 2100. And it may also be that other uncertainties are uncorrelated. So for example, if the reality for the glaciers follows the high-end projections, but sort of other contributions end up looking more like the low-end ones, then it's likely that our probability distributions should be narrower. And finally, we didn't calibrate our projections with observations. This was partly because not all of the data went back particularly far. And we were sort of focusing on creating this broad range of projections. Sort of ideally, and in the future, we'd calibrate projections and use some kind of history matching or weighting approach, particularly for cases like the ice sheets where we had multiple individual studies, where we'd like to sort of give some more influence than others, rather than just taking simple averages. So the other part of our paper was sort of looking at the potential use of our projections. And he was Gonery and Robert created this table on the right, sort of going over the different management problems that require centennial to multi-centennial sea level changes. So our use of scenarios, the ones we use are consistent with either the goal of limiting warming to below 2 degrees Celsius, so SSP 126, or follow the mitigation policies that have been committed to prior to COP26. So that means our projections can be used for international climate negotiations. There's a subset of adaptation problems that these projections can be applied to, in particular to help to avoid lock-ins. So these include land use planning on a broad scale. So helping low-lying areas and countries with how they should plan defense systems. We've got the adaptation of long-living infrastructure. So helping them choose how to protect and sustain their buildings, and then also helping the planning of new infrastructure development. Sort of things said in workshops we've done include sort of new large nuclear reactors, where the timescales they're working in can be really long. A second subset deals with the conserving of cultural heritage and the managing of past industrial activities. So this means that our projections can provide a sort of baseline, no regret scenario. in particular for systems that are deemed of very high value, so sort of cultural places such as ancient cities like Venice, or can help with scenarios where the damage from flooding or erosion is deemed unacceptable and they need some kind of baseline minimum thing they need to avoid, such as the flooding of landfills or polluted soils. So looking sort of into the future and sort of what we've found by doing this, we found that we really need more long-term ensemble projections. So for this study, we only had sort of one study for Greenland that went beyond 2100 and none for global glaciers. So there's still a limit in just how long models are being run for. And our prioritization of sort of parameter perturbed ensembles left us with a really small number of studies to work with. Using simple climate models as they did in AR6, that could allow us for sort of greater exploration of this climate uncertainty rather than sort of the single complex global climate model outputs we're working with or were used in the studies we used. And then there's the fact that the 4 Antarctic studies had really wide ranges in projections. So this arises from the different scenarios used or the different climate model and ice sheet model structure. So for instance, Decanto was the only one, as I said, that had Mickey as a process. And then the issues with adjustments for things such as model drift. Ideally, observations and paleoclimate changes would allow us to sort of explore this model structure and parameterization uncertainty in more detail. Another thing to consider is the different use of scenarios. So one thing we sort of found when it came to looking at the use by stakeholders is that projections for higher emission scenarios would be useful to sort of stress test the resilience of coastal infrastructure, sort of using them as worst case scenarios. We didn't include projections for 585, as I said here. This was for 2 reasons. So as I said, current NDCs suggest emissions aren't likely to follow this sort of high emission scenario for multiple centuries. And there was a very large disagreement between ice sheet studies, which made extending projections extremely challenging. So for the deliverable, we'd done some early extrapolation of the Decanto work under 585, and this was giving us a maximum contribution of over 25 meters. We felt that such extreme projections was going to require a lot more physical justification than sort of our simple statistical methods would be able to provide. Another aspect with scenarios is that we need some intermediates or some medium-high scenarios. So if we're looking at multi-centennial projections, it may be that scenarios such as 3.7 would be a lot more plausible. This would also allow us to check for non-linearity in the response to emissions. So check for any kind of tipping points or critical thresholds being met. And this is particularly important over multiple centuries. And then the extensions of these scenarios need to be consistent. So we need the same scenarios to be used across all sea level contributors to allow for comparison and combination. When it comes to correlations between components, then by assuming full correlation of contributions, it may well be that we've overestimated the uncertainties in this work. So there are alternative approaches. So this includes inducing known correlations with the use of global mean temperature forcing to drive each contribution. Or we could attempt to estimate other known correlations by exploring the uncertainties within model ensembles. So this could be done in a similar way to how Tamsin did in her Nature paper, looking at sort of independent and correlated basal melt sensitivities in the Antarctic ice sheet regions. But luckily for us, it seems that large multi-model projects such as this one are going to help us to explore these relationships in detail. So to conclude, sorry, I feel like I've gone really quickly. But yeah, so we built projections of global mean sea level rise to 2500. And we found the ranges described here for the 2 scenarios. The most uncertain sea level contributor continues to be the Antarctic. And to account for this, we used multiple studies to build our projections. And despite the uncertainties, our projections can be used to analyze sort of their implications for society. and recognize and potentially avoid any lock-ins when it comes to coastal infrastructure. So this paper is still under review at Earth's Future, but if you're interested in a preprint, then the DOI is here, or I can send you a copy if you're interested. And I think that's me done. Thanks.
Thank you, Fiona. Is there some questions? After uploading? Okay, then I will start. At the end, you made a list of further improvements for the community. Did you have a way to quantify which one would be the most important, or quantify by statistical method or by your feeling? So where should we focus first?
That's a good question. I think it can sort of, I mean, it can depend on sort of what aspect of it you're interested in. So yeah, so it's sort of a trade-off, whether you run models for more scenarios or you sort of explore the other uncertainties. Ideally, we'd be doing both, but I'm not sure which one we should be given absolute priority to.
So if we would be able to do only one action, what would be your recommendation? It's kind of a reformulation of my question.
I guess I'd quite like to see more intermediate scenarios being run in the long term. It feels like there's always, I mean, for good reason, there's a lot of emphasis on sort of the high-end scenarios, and a lot of the time it's what the stakeholders are interested in. But if we're not getting any kind of like 245, 370 projections being run, then you can't really see if there's any kind of tipping point or thresholds being met, or any like non-linearity between the emission scenarios. But I'm sure there's people who disagree with me and want something completely different.
So does anyone disagree or agree or have a question? Okay, then I have another one, which is a bit more technical. In the first slides, you show the contribution of Antarctica. Maybe could you re-show the plot? It was slides, I don't know the number, 7 or 8, something like that. Now before, when we see the individual simulations.
Ah. Yeah, sorry.
Yeah, that one. So we see for the UPER contribution around the year just before 2300 that there is an acceleration in the contribution. Yes, exactly below your arrow.
Mm.
Yeah. What is the reason behind? Is the start of a disintegration of a region or something like that? And the follow-up of my question is, could we expect that this kink in the increase could show up later for lower scenario, and then the trend, the choosing trend might be misleading? I'm not sure I'm clear.
Yeah, I think I understand. So this plot was from the deliverable, so it's an example of the DeConto work. So I think this sort of increase we're getting could be from something like Mickey coming into effect as you get at sort of the longer time frames. So I think, I mean, there is a chance that this could then kick in for lower scenarios. I mean, this is for SSP 126, so it's for one of the lowest scenarios. So it could well kick in at a later date. Sort of our choice for sort of taking a gradient that was sort of less than 100% of the last 50 years was in an attempt to sort of represent the fact that we're expecting emissions to reduce, but obviously especially the Antarctic has such a delay in response that it could be that we should have been doing something sort of slightly higher than 10 to 100%, like looking at, I don't know, like 40 to 120% or something like that. But yeah, like this isn't meant to sort of be a like a panacea, like completely perfect projection that has like no faults or anything. Like there's like, we sort of recognize that some of the statistical techniques we use are slightly oversimplistic. We just sort of wanted to do sort of like fast projections to get sort of an idea of what it could be like up to the year 2500.
And you only see this type of kink in the Conto simulation, or others? It's maybe the idea I have behind is would this be pertinent to look finally at the acceleration and try to see if there is a common pattern from one model or the other, and then might help to see on what we should focus on as a priority, coming back to my first question.
Okay, we did look at sort of the distribution of the gradients of like the last 50 years to come up with sort of a slightly more rigorous argument for our methods. And for the most part, we did find that there was sort of a general slight slowing down in those last few decades. So yeah, I'd need to go and double check sort of these plots for all of them, but I'm pretty sure it was Deconto that was having the quite high contributions, sort of that speeding up. And then, like I said, like Lowry had some high projections, but we thought that might be due to some model drift rather than sort of other processes.
Because somehow in the lowest scenario, we also see a small shifts from small kicking from for some of the simulation, and maybe looking at what happens where there is this acceleration. Is there a common feature regionally or in the process? Might be of interest. But anyway, that's enough for me. Other questions? It's time. It's your last chance to ask Fiona. Paul.
Sorry, I always speak too quickly on these talks.
Go on, I'll ask one. It was actually on that same picture you just were showing.
Okay.
I don't know if you can show it again, but it looked like it has two groups of trajectories. There's a low group and a high group. Do you know why it seems to follow two groups like that? And does that give you a way to know how to extrapolate these groups?
That's a good question. That's not something we looked into. And in fact, yeah, we'd probably have to look back at sort of their ensemble design and see what sort of parameter values this group was taking compared to that group to really analyze what it is that's causing this separation. But yeah, that's not something we looked into.
Yeah, because it looks to me like that lower group is just going to curve off like the higher group.
Yeah.
It's just gone later rather than having a different behavior.
Yeah, and jumping in, I would argue that maybe there is three groups.
Like this little group here, and
yeah, it seems that the upper group is the one which has a kick in the contribution 20 years before 2000. Yeah, between 50 and 20 years, 2300.
So it might be that you can get an idea of the long-term behavior by looking at some of the extreme early responses and then extrapolating them later in time for the weaker responders. Do you see what I mean?
Yeah, I see.
Yeah, so look at the early behavior of this group and then try and apply it to a lower group. Yeah, that sounds interesting.
Yeah. Thank you. It's great talk.
Yeah. Gunnery, you sharp. Presumably you have a question or a comment.
I was thinking about what you were saying, and in fact, this acceleration here, maybe, I don't know, Fiona, but maybe you talked about it, characterizing when we have such large acceleration, or we could have such an acceleration. Maybe it could be put in perspective with respect to the time that we estimate is necessary to implement some adaptation actions like estuarine barriers or things like this. So that would be 50 years. And I'm not completely sure if in the final, let's say, projections, we are able to identify specific periods of time where there is a possibility to have such large rates of sea level rise. And in this case, we should anticipate 50 years in advance in order to be ready for adaptation then, or something like this. So that was a bit a follow-up of Gail's questions, actually. But first, I wanted to say congratulations for your presentation.
Thank you. Sorry, what was the question in?
No, the question was, we have talked about these projections, how to do them, what can be, how can they be used, and things like this. But there is potentially another application which comes from the Gail's point, which is at some point in the future we could have some acceleration in the rate of Antarctica melting. How much and these periods of time where this acceleration can occur, I wonder if they can be identified with the perspective that adaptation can take a lot of time to be implemented. So we should be ready to anticipate them 50 years in advance or something like this. And I wonder if there is something to be highlighted here, and if we have actually the possibility to really identify these accelerations, because it's very clear in the Antarctica projections, it's a bit less clear in the total projections.
Yeah, it'd be interesting to see if we could use the projections to do that.
I don't know, maybe it's another study.
Maybe. Yeah, I don't think I'll be adding it into this, but yeah, it's definitely something for sort of the work we're doing with Antarctica at the minute. See if we can try and predict when any kind of acceleration or tipping point or something is going to be coming into effect.
Yes, if it comes from different models, then you start to have a kind of argumentation that it's not an artifact from one model. So, and then maybe you can identify, I don't know, geographical constraint or topographical constraint that they, when we arrive at that point, we might suspect an acceleration.
Yeah.
Then it's maybe a way also to see when this could arrive from lower emission scenario. But I think I agree with Gunnar, it's probably another study, but on the same data sets maybe.
Yes.
Yeah.
Other comments, suggestions, questions? It seems not. So thank you very much again, Fiona, for highlighting us with your work, and it's very, very interesting. Hope that you will have a smooth process in the review of the paper. And thank you all for your time, and wish you a great afternoon, and see you soon.
Bye.
Goodbye. Thanks.
Bye.
Bye, thanks.